Hello and welcome to the very first real video of this channel. Through my long experience I learned that I shouldn't put my light beside me. Anyway, this video is going to be an introduction for a series about electronics, where we will learn about this beautiful world starting from its very basics. The core concept that's behind all of the electric phenomena is called charge. Charge is a fundamental property of matter in our universe, just like energy or mass. Charge is measured in coulombs and can either be positive or negative. The main carriers of charge are known as electrons. An electron is an infinitely small particle which has a charge of minus 1.602 times 10 to the minus 19 coulombs. Together with the so-called protons and neutrons, electrons form atoms, which are the base building blocks for everything in our world. A proton, just like the electron, has a charge, which has also the same value of the electrons, but just with a positive sign. Let's now ask ourselves how charges behave. Since we want to know how two generic charges interact, not just the electron and the proton, but in general, what do they do? Let's just have the charge Q1 and charge Q2 placed at a distance r from each other. They apply a force on each other, which is determined by Coulomb's law. This is its formula. Let's see what it says. First of all, this small hatted r in the end gives us information about the direction of the force. The force normally points outwards, away from the other charge, but this thing might be changed by something. Here we have the product of the two charges Q1 times Q2. If both have a positive sign or both have a negative sign, their product is positive, so the force indeed is going to point outwards, away from the other charge. If instead one of them is negative and the other one is positive, their product is negative, and this minus sign that appears flips the direction of the force, so the two charges now attract. You know how it goes, opposites attract. This other section is a constant because it's made up of constants. Pi is the usual pi, 3.1415. Epsilon is known as the electric constant, which makes you understand how important it is in the world of electricity, and its value depends on the material in which two charges are located. In the vacuum of space, as well as in air that is electrically very similar to the vacuum of space, its value is about 8.85 times 10 to the minus 12 farads per meter. We'll also talk about farads in the near future, not in this video though. Last but not least, we have the inverse square of the distance between the two charges. This dependency is very important because it tells us how the interaction of the two charges is very strong when they are close together, and it's very weak when they're far away. To have an idea of the numbers that we are talking about, let's make a practical example. Let's see how strongly the electron and the proton from an hydrogen atom interact with each other. First of all, as we said, there are two forces at play. The force that the proton applies to the electron and the force that the electron applies to the proton. But the two forces are exactly the same, just in the opposite directions. As we know now, the proton and the electron have opposite charges, so they are going to attract. And we can only calculate one of the two forces. They have the same strength. Again, the two charges have a value of about 1.602 times 10 to the minus 19 coulombs, one with the plus sign and the other one with the minus sign. The distance of the two charges is really not well defined because the electron kind of whizzes around, so it's hard to tell how far away they are. So I just chose a indicative value of about 5 times 10 to the minus 11 meters. If we crunch the numbers, we get a force of 9.26 times 10 to the minus 8 newtons, which is very small in the human scale. This wouldn't move anything. But if you think about the scale of electrons and protons, and especially how light they are, this force is very, very strong. Now, if you had fun, you could play with your calculator and see how strongly two charges interact in various situations. If you did, you'd notice something. Say we decide to have one reference charge, that is here, and see how strongly it attracts or repels a generic charge Q that we place somewhere nearby. Q after Q, R after R, we start to notice something. You could notice, for example, that I'm wearing different clothes and that my setup is different. That's because I'm just dumb and I lost a portion of my footage that I recorded yesterday. But luckily it's not a big deal, I can just record it again. What I was about to say is that example after example, charge after charge, you start to notice something interesting. The only things that change are the charge itself and its position in space. We could isolate the charge and put it aside and group everything else together. This way, we could merge all this first section into a new variable. Be careful though, this new variable is not a constant since r appears in its expression. So what we're going to get is a function of space. We will call this new quantity E. E is what is known as the electric field. As you can see in its expression, the electric field doesn't contain the product of two charges. For this reason, the sign of the single charge is very important. You can think of the electric field as a precooked version of Coulomb's law, which was calculated for each point of space. When you need to know how much force is going to be applied to a charge placed somewhere, you just pick the vector that you left here and then just multiply it by Q. For this reason, a usual representation of the electric field looks like this. As we said earlier, the sign of the charge is important. The electric field of a positive charge points away from the charge itself. The electric field of a negative charge instead points towards the charge. With this new concept in mind, we can now see things in a kind of different light. We can say that every charge has an electric field around itself, and this electric field is what is going to apply a force to any other charge around. This is very cool, but you might be wondering, okay, but what's the advantage of this? We just swap things around. Well, there are a couple advantages. The electric field, as we introduced it, contains the information about the Coulomb's force, but can also contain much more. For example, not only can the electric field be generated by a single charge, but also it can be generated by things like a distribution of charges. And now I'm gonna leave the word to my past self. Moreover, electric fields can also be generated by things that the Coulomb's force doesn't account for. Another cool feature of the electric field is that it is the protagonist of Maxwell's equations, which are a set that are definitely, with no doubt, among the top most important equations in our universe, since they regulate all the electromagnetic phenomena. We will talk about them later, but just know that they are fundamental and the electric field is a protagonist. The electric field, though, has a big downside, which is that it is very complicated. Not only is it hard to calculate, but it also gives complicated results. So the last thing that we want is to use a tool that is so complicated that even the simplest of problems requires weeks of computations. Since the electric field is fundamental in electronics, it's behind everything that happens, we cannot just set it aside. We will talk about it when it is the protagonist of our ideas, for example when we want to build an antenna, or when we need to understand how components work, like in the case of capacitors and transistors. In all the other cases, we need a tool which can give us all the information that we need, so which is bound to the electric field because, again, it's necessary, but in a simpler form. This other tool is kind of the backside, in some sense, of the electric field and is known as voltage. But we will talk about voltage in the next video. Thank you for joining for this video and hopefully see you in the next one.